Hello, everybody. Welcome to today's webinar, Unlocking the Potential. I am Amanda Harmoning. I am an admin assistant here at AERA, and I will be moderating today's event. And joining me from the AERA team is Rob Monroe.
Hey, everyone. Yeah, Rob Monroe here. I look after membership and technical development at AERA. And both Amanda and I, we're going to be in the background today. We're going to help answer any questions you may have throughout the webinar. We're going to leave lots of time at the end. So if you have any questions for Lake, go ahead and put them in that questions box. As well, if you got any questions about AERA or any upcoming events that we're doing or anything like that, EP Magazine, go ahead and put those in the questions box as well. So what I'm going to do is I'm going to go back to Amanda, and she's going to show you how to use that control panel. It's in the upper right part of your screen. And yeah, we'll talk to you here in a bit.
All right. First off, there are a couple different ways to listen in today. You can either listen in via phone or via your mic and speakers. Make sure that you select the appropriate radio button, and if you are listening in via phone, be sure to enter that audio pin. This just makes sure that your line stays muted and that we don't have any issues. Also, if at any point during one of our webinars you experience any audio problems, you can always let us know in the questions box or shoot me an email at amanda@aera.org, and I am always in the background working to help get those resolved. A couple other things quickly. The grab tab is that little orangish box with an arrow. You can use this to collapse and expand the control panel. This just gets it out of your way so you can view the presentation in full screen. And then the question chat box at the bottom, this is where, as Rob said, you can ask us questions, ask late questions, anything like that. Go ahead throughout the webinar anytime you have a question and just drop it in there, and we will be asking some of those live during the Q&A at the end. So at this time, I'm going to hand things back over to Rob and get going with today's presentation.
Awesome. Thanks, Amanda. So just a couple housekeeping slides to go through. We'll keep it short so that we can get Lake on. So for his presentation, what we're going to do is we've had to reschedule some of our 2020 regional conferences, and unfortunately, the SCAT conference, we had to postpone that one, as well as we've had to postpone the Hastings Piston Ring conference. So what we're going to do is we'll keep you posted on what we're doing with those. So keep an eye out, and we'll let you know what date those get rescheduled at. We still have the Sun and Goodson Regional. That's August 11th, and that'll be out in Winona, Minnesota, as well as we still have the Dallas, Texas, the EPWI, October 16th out in Dallas. So those are still on as well. Now, what good news is that we've got both SCAT and Hastings. They're doing a webinar for us, so that's coming up here in the next month or so. So we'll keep you informed with all the technical information that you need to know about that. Now, the really good news that we've got is knowing that we can't bring the regionals, we can't get to them right now due to travel restrictions and that kind of stuff. We have got an event that we're calling the Engine Professional Super Webinar. So this is going to be on May 15th. It'll be at 11 Central. And what we're going to have is we're going to have Total Seal, Comp Cams, Ben from EFI University. They're going to do 4 30-minute presentations with 4 30-minute question and answer sessions. And this is going to be a really, really good event. You want to free up some time for this one. To have 4 of these gentlemen to be able to, do a live Q&A with and ask any questions that you want throughout the day is really exciting. So we want to thank everybody over at Total Seal, Comp Cams, and EFI for helping us put this together. And a couple ways that you can register for this event. I mean, you can go out to our Facebook page, out to our Instagram page. If you want, you can email me at rob@aera.org. Or even if you want a link to this webinar, simply let us know in the questions box today, and we will get you the link to your email address and make sure that you get looked after there. So a really exciting event, and like I say, that'll be coming up next Friday on May 15th. The other thing that we got, just to let you know, so right up through till summer, this is how it's looking for our webinar dates right now. So we've got the super webinar next Friday. We've got on May 21st, SCAT crankshafts. So Tom is going to talk a little bit about the history of the LS crank, as well as some balance and reluctor ring challenges that you may experience when working with this crankshaft. June 2nd, we're going to have Greg Arsenault from AMBAC International. He'll be talking on failure mode analysis with turbochargers. And then our last one just before summer starts is going to be the Hastings Piston Ring webinar as well. So Again, if you want to be sent a link to any one of these webinars, or if you want more information, let us know in that questions box, and we will get you looked after there. We also want to let everybody know, even though with COVID-19 and everything that's going on here at AERA, we are still working 100%. So we still have, we've got staff at headquarters, as well as some of us here are working from home. All 5 techs are working. So you can still reach us by phone, by fax, by email, and our hours are 7 a.m. to 6 p.m. Central, Monday through Friday. So again, we're here looking after you to get all the information that you're looking for. The other thing that we've got, most of you definitely should have got your second quarter edition of Engine Professional magazine in the mail by now. I know I did see some social media stuff from our international members, and it is delivered over there now as well. So the one thing I'll mention is that if you want a copy of Engine Professional magazine and you're not receiving it right now, again, let Amanda know in that questions box, and she'll get that sent to you. So you can get us, we'll get you on the mailing list and get Engine Professional over to you. So the other thing that I'll let you know too is that if you go to www.engineprofessional.com, you can read the digital version of EP, as well as you can look at any of the archived copies of Engine Professional dating right back to the beginning. So there may be an article or two in there that you saw a couple years ago. And if you want to read that, you just go out to our website there and you can read any one of those archived articles. So it's a great way to, especially right now, all of us have a little extra time in our hands. So good time to hone in our skills and catch up with a good technical information. All right, so I've got one last slide here, and then we'll get on with today's presentation. AERA, we do have an online training program, and so this is a comprehensive program that we give you 1 year to complete. It's $150, which includes the book. When you're finished, this gives you your engine certification, like your engine machinist certification, as well as your cylinder head machinist certification. And this looks really, really good on a resume. Or maybe you've been doing machining for years, and this is a perfect time to maybe just brush up on some of your engine theory and some of those skills. So it's a great program. Like I say, you've got 1 year to complete it, and it looks really good on a resume when you're all finished. So, all right, well, let's get on with today's webinar, Unlocking the Potential. And we've got Lakespeed Junior from Total Seal Piston Rings. Lake is the Vice President of Sales and Marketing over at Total Seal. And a lot of you know Lake. He's very well known in our industry. It's always a treat to have him come on, and we're looking forward to today's presentation. So, hey Lake, how's it going today?
I'm good. However, I got to look here, right, and then wave over there. I got to move my box around so I don't look like a total idiot. There we go. That's probably a little bit better. Hopefully everybody can see the webcam. Figure it might be a little better.
Looks good. Yeah, you're good to go.
Yeah. Hello from my basement here in North Carolina. So I guess we should go ahead and get started then, right? That's the problem with everything these days, is that everything's just so relaxed. But like I was telling Rob and Amanda earlier, for the whole world being shut down, I feel busier than ever. Just the number of phone calls and emails, every day is tremendous. And like the guys at AERA who are still working, fortunately, Total Seal, we're still working too. The shop out in Arizona is deemed an essential business, fortunately, and so they're still working away. Phones are busy right now. I can look over and see that Kevin's on the phone with somebody right now. So it's pretty great. It's we're very fortunate to be able to continue to operate and continue to work and get things done. And we're hearing great feedback from machinists and engine shops like yourselves that are watching today, that they're still got engines coming in and still work to be done. So that's a great thing. And really, really excited that NASCAR is getting back to racing at Darlington this month. And if you know anything about my dad, Darlington's a place that's near and dear to our hearts. I happened to be at Darlington in 1988 when Dad won the Trans South 500 there, and his number 83 wins Kmart Oldsmobile. That was awesome. So a little bit of throwback there. So great to be having the season kicking back off, and I hope that's going to be able to help kind of turn the tide, and many other people kind of say, hey, we can go racing, and things going to get closer back to normal again. So it's a good thing. So I guess with that, Rob, I should probably get in the presentation, right?
Sounds good. Whenever you're ready.
All right, so killed enough time. Let's get going. As Rob said, all right, I'm gonna move on here. I am Lakespeed Junior, and again, several of you guys know me from being around the industry for a long time, of course, because my dad, that's him in the blue helmet back there behind me. Of course, he's not there behind me very long. Dad's so super fast, and we're actually really hoping, that's us doing the vintage go-kart racing stuff, and really hoping to get up to Newcastle, Indiana in June for the vintage nationals up there at Mark Dismore's track, and get those go-karts back out there and smell some two-stroke oil and methanol. Actually, the best thing we'd run is we run castor bean oil. So the smell of castor bean oil and methanol is just like the best smell in the whole world to me. Just, it's great. So hope we get to go be doing that. And, that's obviously my background is, for those who don't know me, my dad was a NASCAR driver, grown up around racing my whole life. Was the head formulator at Joe Gibbs Driven, did all the testing and development on the motor oils, and gear oils and everything else on the Gibbs program. Very fortunate that, the products that I helped design and test, won many championships and many races around the world and various series beyond NASCAR. And so I kind of look at engines from a different perspective. There's guys, next week, things are going to be fantastic, by the way. Just a little plug, the super webinar, next Friday, make time for it. It's going to be worth it. I mean, it's, one, if you've ever heard Billy Godbold speak, you will learn something. Ben Strader, you're going to learn something. My buddy Keith Jones, who I get to work with now, is just, he's the ring whisperer. I mean, the guy just knows so much, and he's so sharp with these things that it's, and I'm just going to talk about oil for a little bit. It'd be kind of fun, but it's going to be fantastic. So mark your calendars, register today, do it. It's going to be worth it. So with that kind of plug out of the way, for that, really when I look at an engine, I look at it from the eyes of a tribologist, and we're going to talk a little bit about that today. And then, my section of the presentation next Friday is going to be more of a deep dive into tribology and why you should care about tribology and how that influences your engine. And maybe it's a little bit of an expansion of what we're going to talk about today, and kind of looking at an engine from the eyes of a tribologist and what that means. So with that being said, we'll move forward a little bit. In case you are wondering how my dad is doing, dad's doing great. I'm actually going over to the shop tomorrow. We're going to be dynoing an engine. We got these little, air-cooled two-stroke engines. We got a water-cooled four-cycle. It's like a 12,000 RPM, 250 cc engine that we're going to be kind of getting going, that I plan on doing a lot of ring testing with, so that we have some data, so we can go in and maybe try different things, like different back clearance, different side clearance, and be able to document those results. That way we can share with you guys what we see. And it's not that we're sharing somebody else's information that's proprietary. We can give you real information on a single cylinder engine where we don't have anything else going on. There's no crosstalk in the manifold or anything like that. It's pretty straightforward. We can go there and do things like that, and then say, hey, here's what we see. And then it's data you can use to make you hopefully improve the efficiency of your program, which is what we're all about. So, yep, Dad's doing really good. Just by the guy in the red suit over there isn't actually me. That's my son Benjamin. Dad giving him some lessons this past summer, and hopefully this summer we get to go out the racetrack and continue that education for Ben. Dad's still so super fast. It's crazy. So to the meat of the presentation, what were we talking about? Tribology. I've kind of thrown that word out a couple of times. Tribology is the fancy word for the study of friction, wear, and lubrication. I'm a member of a group called the Society of Tribologists and Lubrication Engineers, and within that, I'm one of less than 1,000 people in the whole world. that's a certified lubrication specialist and oil monitoring analyst. And then you get into all the other stuff I've done, and it makes me I'm an oil nerd at heart. I really am. But I love engines. My passion is engines. And, that's really why working at Total Seal is so great, is that, I'm not tied to any one, brand of lubricant anymore. And that's a nice thing. And all of that information does apply. And when we get to talking about ring seal, which is going to be the real heart and the meat of the presentation today, you'll kind of see that, ring seal is part of that. Ring seal is the essence. It's the real key to the efficiency of the engine. And oil is part of that process. And we're going to talk more about that, later in the presentation. So the, tribology is that study of friction, wear, and lubrication. So the lubrication is part of it, but there's more to tribology than just oil. It's also about wear and friction. And that's really where, getting to work for Total Seal is fantastic, because piston rings happen to be a severe or major contributor to all of those things. They have a definite influence on friction, they have a definite influence on wear, and because of an oil control ring, it plays a role in terms of lubrication in regards to the cylinder wall and how a piston ring seals up. So with that, let's get moving forward and kind of go over what we're talking about in terms of efficiency. So when we're talking about efficiency, we got to kind of begin with a fundamental understanding of the engine we'll call it from a chemical perspective. Because again, I'm a tribologist, I'm a chemical guy, but I love engines, and I look at engines as a chemical reactor. An internal combustion engine reacts air in fuel to create heat energy. That heat energy, that expansion is what moves the piston. That's what creates the force that makes power. Okay, so we're taking that heat energy, we're converting it to useful work. From that perspective, the energy potential of an internal combustion engine is basically limited by the amount of air and fuel the engine can process. Okay, the old school way we talked about things, right? There's no replacement for displacement. The bigger the displacement of the engine, the more air and fuel it can process. Of course, you look at a small F1 engine, you're like, well, they make tons of power, but very small displacement, but they're processing the fuel more rapidly. When Ben talks next week, he's going to have some great information, which is why, again, back to sign up for the super webinar, because part of this thing is, okay, how much air, how much fuel can you process in a given amount of time becomes the energy potential of the engine. And that's really a great way of looking at it, because it's not about how big the engine is necessarily, right? It's how much energy potential can I process, right? The more air and fuel I can process in a given amount of time, the more energy potential lies in the engine. So if we take that as the beginning point, now we say, okay, there is a set energy potential for an engine. How much of that energy potential is actually moving the vehicle? How much of that actually leaves the engine? This slide here, from our buddies at Chevron Phillips, shared it with me, actually comes from a Department of Energy study back in 2008. Just last year, Ford Motor Company released a study that has basically almost identical results. So, 12 years, 11 years later, Ford releases a study where its findings are pretty much mirror what the 2008 study did, and both of them point to one key thing. If you begin with the energy potential of the engine, 35% of that potential blows straight out the exhaust, which is why turbochargers are so popular now at the OE level, because it is the lowest hanging fruit in terms of improving the efficiency of an engine. You're taking that heat energy and you're returning it back into useful work that would have just blown out the exhaust and gone to nowhere. 30% of that energy potential is, gone through the cooling system. I won't call it wasted, but it's not moving It's not being used to move the piston. It's just, wasted out through the cooling system. That leaves 35% of the energy potential actually moving the piston. Of that 35%, only 23% actually makes it to the flywheel, leaves the engine. So there's 12% of that energy potential is lost within the engine. Now, half of that is just in air pumping. It's a 4-cycle engine. There's just wasted energy because of being a 4-cycle. That's just pretty much a fixed deal, right? Half of that, though, that other 6%, is pretty much engine friction. And 45% of that friction is the piston ring and cylinder wall interface, or 46% if you follow the math right here. So if you look at it, of that energy that is moving the piston, the frictional losses, almost half of the frictional losses in the engine come down to the piston wall the piston ring to cylinder wall interface. So as a tribologist, guess what is the lowest hanging fruit in order to reduce friction and improve efficiency? Piston ring, right? So that's why I'm so excited to be working at Total Seals, because, as an oil guy, you're like, okay, well, I have some part of that, but the biggest chunk is the piston ring. So if I can improve how the piston ring is interacting with the cylinder wall and the piston itself to improve ring seal, reduce friction, now I can really take a sledgehammer, not just a ball peen hammer, to this problem and really unlock a lot of potential and increase the efficiency and durability of the engine. So that's really where the lowest hanging fruit outside of a turbocharger in terms of efficiency is the piston ring. So the tools we can use to do this are going to be, one, trying to reduce friction, right? And we're going to get into what that means and how piston rings can reduce friction. Then the other part of it is going to be ring seal. Back to that single cylinder engine we're going to be dynoing tomorrow. That's one great thing about a single cylinder engine. There's nowhere to hide. When I was doing the development work on oil formulas at Gibbs, we had a single cylinder engine, for the motocross team, right? We had a dyno for the motocross team. I had a single cylinder engine, and that's where everything would begin in terms of oil testing. And you could sit there, and we had a little lab, and we could sit there and blend up an oil, run downstairs and pour it in the motor and run the engine and see what it did, and run back upstairs and change the formula and run back down. And it was great to be able to do that. So, but that single cylinder engine is fantastic tuning tool. In fact, most Formula One engine development is all done on a single cylinder engine, because a V8 essentially is 8 single cylinder engines, and if it's a common blend and manifold, that's what ties it together. If you look at an individual runner engine, there's not as much crosstalk on that, because there's not, they're all 8 individual cylinder engines with individual runners. So those are the kind of things we look at, is trying to say, okay, when you look at an engine and you're trying to improve the efficiency of that engine in terms of ring seal, is a big part of that, because everything that blows by that piston ring is wasted energy. So you want to have the best ring seal, and you want to have the least amount of friction. And that goes back to what we learned at Gibbs with restriction plate motors. Yeah, I've said for years and years and years, when they put that plate on those engines back in 1987, I believe it was, end of 86, that's when the cup engine programs took off. That's where we learned so much on a plate engine. That's where aerodynamics really became big, is that Daytona Talladega, that was what it was all about. I got a picture over my wall right over there of the number 92 car from Talladega winning the pole in 2001. That's pride. The camshaft on my desk that you can't see is right over there. Daytona motor that Mark Cronquist gave me, from Daytona one year. I love plate racing, not because I think plate racing is great. It's because that was the challenge where it wasn't the driver, right? It was the engine in the car. It was everything. The faster that car was, the better it could be. And it wasn't about handling and all that. And I know there's shot guys and all that, and let the shot guys and the chassis guys do their thing. I'm wide open throttle, fast as we can, make as much power as we can. And the plate program is really where we found things. And, while I may be new at Total Seal, my relationship with Total Seal is not new. It goes back to when I first came to Gibbs, and we were running, 0.8 millimeter rings back in 2004. Today we're running 0.5 millimeter rings, 0.8 in the 1,000 horsepower desert off-road truck engine. So my experience in history goes way back with Total Seal because of our relationship with Joe Gibbs Racing, and the fact that every Joe Gibbs Racing engine built since 2002 has had Total Seal piston rings in it, and not a single one of those were a gapless ring. So when we're talking about Total Seal, please don't confuse that Total Seal and gapless equals the same thing. The majority of the piston rings we manufacture are not gapless. Now, in fact, myself personally, I've never used a gapless ring. I mean, I know, like Ron Shaver and Don, I think Don, you're watching. Hey, buddy, they use gapless rings, second rings in the methanol, injected alcohol engines, because for dilution contamination control, and that's, we can talk about that later in the seminar. But that's really my experience, my background with Total Seal is my relationship at Joe Gibbs Racing, and then the time we spent doing oil testing at Shavers. We were using 0.7 millimeter rings in that engine. So I kind of jumped ahead of myself there. We'll get to that in a minute. But really those are the tools that we're trying to deploy here in order to increase efficiency. Is we want to reduce friction and we want to improve ring seal. And if we can do those two things, we're going to improve the efficiency of the engine. And the tools do, and how we kind of look at that. And this is really what I'm going to talk about next week. So if anybody happen to be that's on here, if you happen to be on the webinar recently, Andy from Line to Line talked a little bit about the Striebeck curve and how the piston skirt coating was a way of influencing and shifting the Striebeck curve. So my section of the super webinar, yep, here's the third time, right? Going back the third time why you should sign up for the super webinar. What I'm going to do is a deep dive next week on the Striebeck curve. It's all going to be about tribology, and we're going to look at the Striebeck curve and really get into the details and show how those changes in surface finish, speed, load, viscosity, how all of those things factor in to changing the shape of the Striebeck curve. Because the flatter that curve is, the more efficient your engine is going to be. Let that sink in there for a minute. You see that curve on the screen, and you see how to the left of it, it's really high up, and then it flattens down, and then it starts to go back up again. The flatter that curve is, the more efficient your engine is going to be. So what we're going to talk about next week is the tools to flatten that out. We know that in that boundary condition, friction is going to be very high. And in that boundary condition, that's where you have the highest level of load, the lowest speed. And then on the other side, you see the friction coming back up as it rises to that hydrodynamic region. You see that friction begins to increase the further you go to the right. And that's where the oil films get thicker and thicker and thicker, the higher and higher speed you go. One interesting thing about a piston ring, because we're going to go into the details of all that again next week, and I won't waste the time now getting into that. The thing to know is a piston ring is the only device in the engine, the only part in the engine that actually experiences all 3 stages of lubrication on every engine cycle. You know, a camshaft's gonna, be in the boundary condition the majority of the time. Every degree of lift is gonna be in boundary condition. It's gonna be in the mixed condition on the base circle. Your engine bearings are always gonna be running in hydrodynamic except at startup. But the piston rings are gonna start off, think about a piston. Let's start at mid-stroke. Mid-stroke approaching top dead center on a compression stroke. At mid-stroke, that's the highest piston velocity. I think if I remember the math in my head, it's like over 1,500 feet per second. It's like stupid fast, right? There's an article in Engine Professional magazine where I did all the math, and it's coming out, I think, the 3rd quarter issue, where we calculated all the speeds and listed this out so you can kind of get an understanding of it. But that mid-stroke, that's your highest surface speed of the piston ring and the piston itself. In that condition, that piston ring, it's a ski, right? It's operating in hydrodynamic, full film condition. But as the piston approaches top dead center, 2 things begin to happen. One, starts to slow down, but also as it approaches top dead center, cylinder pressure is building. The Strybeck curve is viscosity times speed divided by load. So in the operating environment, operating temperature of the engine, the viscosity is not going to change. It's a fixed value at that point. Now, obviously, engine gets hotter or gets colder, that can change, and you can change that by changing the oil. But in the engine for a given moment of time, given a cycle, viscosity is going to be the same. What's going to change is your speed and the load. And as you decrease speed of the piston as it nears top dead center, and you increase cylinder pressure, that's increasing the load, because that cylinder pressure is getting behind the ring and forcing the ring out and increasing the load of the ring against the cylinder wall. For those 2 reasons, you're going to move from that full film into that mixed film. Then you're going to move into boundary condition. But you think about it, when you look at the bore of an engine that's been run, where's all the wear? Well, it's pretty much in your top dead center and your bottom dead center, because those are the areas the lowest speed and the highest load. Obviously, there's more high load at top dead center than bottom dead center, which is why there's more wear at the top of the bore than the bottom of the bore. So that's the perspective to kind of look at how the ring is interacting and that tribology focus and perspective on the engine. So what are we going to do about it? Okay, the best way to reduce friction is to reduce surface area. You think about it. You go out to Bonneville, all those streamliners, they're streamlined and they're small. Why? They're not like Mack trucks. It's surface area. The smaller the surface area, right, the least amount of drag. Anybody that's gone skiing, knows that, that the fast downhill skiers ski on thin skis, not big giant snowboards, right? So when you go from, say, an 0.43 ring to say a 0.9 millimeter ring to say a 0.7 millimeter ring, which is what we did at Driven with our little test engine we had there at Shaver Specialties. They built that motor and allowed us to use that engine. We call it Oscar. It's been running forever. And we started off initially with Oscar with 0.43 rings, and we would do all the testing. And I'm going to show some slides later, and I'm sure Billy will talk about it some maybe next week. That to do oil testing, we wanted to make sure we were doing the right kind of wear measurements. So a flat tappet cam engine is a great engine to measure wear with, because you can take an ad coal and you can measure the cam lobe, all 16 lobes. What we were able to do with that engine is take, have Billy and those guys do cams for us, measure all 16 lobes, put it in the engine, break in the engine, run it for 30 minutes, get everything broken in good, pull the cam back out, ship it back to comp, have them measure all 16 lobes again. Then we had a baseline to begin with. We already knew it was already broken in. Then we could run a 2 to 3 hour race simulation on that cam, then send it back and have it remeasured. And then we could do that, we could do 2 of those a day out there at Shavers. Once the cams are broken in, we could show up, boom, 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 break in, run these back-to-back durability tests, and then send the cams back to have them checked. Well, one thing we found when we started off doing that with the 043 rings is that, you run that test day after day after day. Well, you come back as the engine would run, you'd see a change in power over time. As you just think about it, if you do 2-3 hour race simulations a day, well, that's 6 hours of engine runtime a day. You do that for 5 days, that's 30 hours of runtime. There's 30-something pulls. You could be well over 300 dyno pulls in a week. And you're trying to look at the differences between not only the wear differences between different oils, you're doing oil analysis on that, but you're also trying to look at the power levels. And you're seeing the power levels drop off over time. You're like, well, are those oil formulations not as good? Or is it something about the engine giving up? So as we went forward in time, and we're working on different things, we went from 043 rings to the 0.9 millimeter rings. And that made a big difference in going from an 043 ductile moly face ring to the AP steel ring. That was a huge change in the consistency of the engine. Going to the 0.9 millimeter consistency was just way better. It was also about 8-10 horsepower better, horsepower wise. And we're like, wow, that's kind of cool. It just got better. And then the key thing is it stayed better. The best thing we ever did, we were working on some braking oil formulations, and I called up Keith and I said, Keith, what would be the hardest ring combination to break in a wet sump motor? And he's like, I can send you a tinitride coated, face coating 0.7 millimeter ring. If you can get that thing to break in, you're really doing something. That's going to be pretty tricky to break in, a 0.7 millimeter, tinitride, real hard face coating ring. I said, all right, cool, send it to us. We give it a go. So we actually, put it in, ran it, and got her to break in, and it was like, awesome, this is great. Once that thing bedded in, and there's a story on that later, that became like the Swiss watch engine. It didn't vary. No matter how many runs, it could be the 300th pull or the 30th pull or the 330th pull. If you had the same oil in there at the same temperature, water temperature, you got the same number. You just Swiss watch consistent. Now, the key thing with that was, when we went from the 0.9 to the 0.7, it gained another 10 plus horsepower. So we saw a 3% increase in efficiency just by changing piston rings. That was pretty incredible. You also think back again, the NASCAR stuff. You went back in the old days, 043 was thin. Today, 0.5 millimeter in those short blocks live forever. So one of the things you can do, reducing friction. If you can go to the smaller, thinner ring, you can do it, and it will increase horsepower, period. You look at the days, the new LT engines from Chevrolet that are going in the Camaros and the Corvettes, 0.8 millimeter rings from the factory. Think about that. In the old days, 16th ring is, roughly about a 2 millimeter ring, rounding there. You go from 2 millimeter rings in the old days to 1.5, down to 1 is pretty common. If you get pistons from Mala or pretty much anybody anymore, there's, either 1 or 1.2 is pretty common on a shell piston these days. Now the OEMs are as thin as 0.8 millimeters. So why? Friction reduction. You're going to smaller rings to reduce friction On the OEM level, they're doing it for fuel economy. So a way to gain power and performance improvement. But I will also say this too. One of the things we noticed in that same engine is that it increased durability. And one of the best comparisons we did was, when we were developing the GP1 oil, one of the things we saw with the GP1 engine oil was, okay, we're going to do this oil and we're going to need it to do the flat tappet test. We ran the flat tappet test at Shavers. But when you're developing oil, it's not just going to run in a flat tappet motor. You got to test it in a roller cam motor to see. So you think about it, that roller cam engine, back to the Stribbeck curve, the flat tap is going to be in that boundary condition. Roller cam's not going to be in that same boundary condition. Reason why is because of that roller wheel moving. And just like a wheel on a tire, right, what does it do? It deforms, flattens it out. You think about hydroplaning, right? You get, if there's water between the tire and the road, it's actually gonna, that deformation is gonna, hydroplane is gonna lift. That's why we have, groove tires for the wet. We don't have groove lifters, not lifter wheels, right? And what happens with that oil is going to be between the wheel and the cam lobe. Now there's surface roughness there, but that oil is going to be trapped in there, and it's going to actually basically maintain that mixed film condition. So to account for that, we had to run the same oil in the flat tappet engine and also in a roller cam engine. So we actually bought LS engine, one of the CT 525 engines, and we ran the same oils in both the flat tappet motor and the roller cam LS motor, ran the same durability cycles, and then took oil analysis samples from both engines. Because obviously the flat tappet is very easy to measure the wear, like I said before, with the AdCol, but it's a lot more challenging to do that with a roller cam engine. So the way to determine wear in the roller cam engine was to do used oil analysis. So what was interesting is when you looked at the used oil analysis results, the flat tappet engine had less wear metal, had less iron in the oil. Well, that makes no sense. That's completely counterintuitive. You would think that the flat tappet motor operating in boundary conditions and all that would have generated more wear than a roller cam engine. Here's the difference. The roller cam engine had 1 millimeter, 1.2, 1.2, 3 millimeter oil ring package in it versus the flat tappet motor having a 0.7 millimeter diamond finished, ring package. The difference, same amount of dyno, 350 dyno pulls, same oils. One's 2 parts per million, one's 4 parts per million, and then you look at the leak down, and that's where the proof was in the pudding. The 0.7 millimeter ring engine only leaked 6.75%, whereas the roller cam motor was 10.25. The increase in wear was due to an increase in bore wear. It wasn't the valve train that was causing the higher levels of iron. It was the cylinder bore wear, because a larger ring is a bigger file. That's simple, right? Even if the surface finishes were the same on both rings, which they probably weren't, because one was a diamond finish ring, but if you had a larger ring of the same roughness, it's a bigger file, it's going to remove more material. And when you go to, a diamond finish ring with a smoother surface finish, it's like going to a higher grit sandpaper, right? It's just smoother, it's going to wear less. So those are the things to think about, that you can change friction and you can increase durability. Going to a thinner ring doesn't mean engine durability is compromised. In fact, we've seen the exact opposite. When you go to a thinner ring made out of steel versus cast iron, that material difference is huge. And that steel ring is going to have PVD applied face coatings, which are going to increase the durability, because those are basically, essentially, that coating, a dry film lubricant. So you're putting the oil where it's supposed to be, not the oil, but you're putting a lubricant where it's supposed to be, when it needs supposed to be, so it can protect that surface and provide increased durability, so you can increase horsepower and increase durability, longevity, without any compromises, by improving the material selection of the ring, the coating of the ring, and then optimizing the size of the ring as a way to unlock the efficiency of the engine by doing that. And really what that comes down to is, I look at that ring seal is like a soup. And that's one thing we saw with that motor, is that you're trying to increase efficiency. Well, the soup, isn't just the broth. It's not just, the meat. It's not just the vegetables or the spices. All of that has to come together to create the soup. Ring seal is the same thing. It's not just the piston. It's not just the cylinder wall finish. It's not just the ring. It's not just the oil. When you think about oil as part of this soup, you got to think about it like a gasket. All right. If you've got a cylinder head and you've got a block, you wouldn't just bolt them together without a gasket and expect it not to leak. The gasket is there to fill in the valleys between the cylinder head and the block, those surface irregularities. That's what the oil does. The oil is the gasket between the piston, between the ring, between the cylinder wall. Because those are all metal objects. They're all going to have surface finish. What's taking up that gap, filling that void, is the oil. That's why the oil is part of that process. It's part of that ring seal soup. Other part of that ring seal soup is, ring seal itself. How does the ring seal? Because that's all a piston ring is. It's a seal, right? The leak paths are there's three main leak paths. The first one is the end gap, right? That's what Joe Moriarty started Total Seal doing, right? Was we're going to address the leak path number one by creating a gapless ring. That way we seal that gap by having the overlapping ring. That was the whole idea of the gapless ring. But that's not the only leak path, right? Leak path number two is actually around the ring groove. And that's where the diamond finishing ring came in. That's where, when Total Seal got into NASCAR at Gibbs, that was what the selling point was the diamond finish ring. You get that ring groove as flat and smooth as you can, then you need to have a flat, smooth ring to seal up properly. You look at the diamond finish ring and how smooth it is. You look at a cast ring, the RA is around like 4. You go to, which isn't bad, right? But you go a diamond finish ring, it's 0.4. So it's a fraction of the surface roughness. Smoother, flatter, better ring seal matches up. And the last thing is your leak path is past the face. A little history. So a guy named John Ramsbottom, an Englishman, in 1852 invented the piston ring for a steam engine, right before the internal combustion engine was even developed, right? So the idea of the piston ring has been around for a long time. And that leak path, past the face, you're trying to deal with that. And in the old days, when engines had low compression, you could have really high ring tension, and that would basically do the job. But in today's higher compression engines, it's not the ring tension that's creating the seal. It's the gas pressure getting behind it and forcing it out. You're thinking about 1,500 PSI of cylinder pressure. 20 pounds of ring tension is not going to seal that. You've got to get the gas behind the ring, utilize that gas to push out to seal against the piston wall or cylinder wall, right? That's the only way that ring can seal that groove to the cylinder wall, is by having the gas pressure behind it. And of course, that's where gas porting's been around. That's the whole idea of gas porting. Been around since at least the 70s, and started off as vertical gas ports. And of course, the problem with vertical gas ports, is that, gasoline, they get dirty. Gasoline is a blend of molecules. So, there's a distillation curve with gasoline because it's a blend. There's small hydrocarbons and there's large hydrocarbons. And what you typically see, the carbon buildup that you see in a gasoline engine, is the larger molecules that have not been burned. You know, again, that distillation curve, if it doesn't vaporize, it can't burn. That's why diesel engines create so much soot, is that the heavier hydrocarbons in diesel, because there's such a small window for it to, of injection for it to vaporize, it doesn't vaporize. It's still liquid under the heat. It carbonizes. That's what creates it. That's why direct injection engines make soot. Anybody that watched the webinars we did about direct injection, you'll know that, right? It's that amount of time. You got to vaporize the fuel for it to be able to burn. If it doesn't burn, it just becomes carbon. So that's why gas ports would block up, which is why methanol, a single molecule, runs so much cleaner. Not because it's a better solvent, that's part of it, but the main reason why, single molecule versus blend, single distillation temperature versus a boiling range. That's why it runs cleaner. But when you go to a lateral gas port, that was kind of the solution for, you know, not having vertical gas ports. Lateral gas ports, again, been around for a long time, work really great. It's ring jujitsu, right? You're using that gas pressure, getting it behind the ring to force it out. So now I can lower the static tension of the ring, reducing friction. Remember, though, the calculation on the Strybeck curve, that friction is a, you know, calculation of viscosity times speed divided by load. Take away ring tension, I drop some of that load, I reduce my friction. The downside of lateral gas ports are you're going to end up, well, one thing, you're putting a hole in the side of the piston, right? So you're taking that top ringland and you're putting a hole in it. Inevitably, to have equal distribution of the gas pressure, you have to have a gas port near the exhaust valve relief, which means you've made the weakest part of the piston even weaker by putting a hole in it. Well, the solution to that is a gas ported piston ring. And we've been doing these for several years now at Total Seal with the highest end teams. Actually, it's just the next evolution, right? You're using that same concept of gas pressure, that ring jujitsu, using the gas pressure to help you as opposed to trying to fighting against it. But now, as opposed to having to put the hole in the piston, you're putting it in the ring instead, which isn't a problem because this ring is made out of either, you know, tool steel or stainless steel, right? You can even do it in the larger cast rings if you needed to. They're ductile, but really it's about putting it, you know, in the steel rings. And the advantage of that is twofold. One, now you're not putting a hole in the piston. Number two is the piston ring is actually in contact with the cylinder wall and it is rotating. And that's the real key difference. Because that ring is rotating, now the gas pressure is actually being put and spread all the way around the cylinder bore as opposed to always loading one area. You know, it's pretty common that they said, okay, well, you can't run a gas ported, you know, piston, you know, in a street engine because, you know, it's going to wear the bore out. Well, the reason it wears the bore out isn't because it's gas ported, it's because it's pushing on the same spot on the bore over and over and over again. Anybody that's ever honed an engine that's got gas ported pistons, you'll know first stroke down, you can see the witness marks of where the gas ports are because it's only loading the same area. With a gas ported ring, it doesn't do that. It's moving it around, so it's more even bore wear. Back to being a tribologist and oil guy, other thing I can tell you is the detergents in the motor oil that keep things clean are more effective on steel than they are on aluminum. In fact, they're not effective on aluminum. So one thing is the motor oil detergents can actually keep the gas ports in a ring clean where they can't in a piston. So that's another advantage right there is that, you know, by having the gas ported ring, you can utilize that chemistry advantage and mechanical advantage to get all the benefits of gas porting without the downsides of what we've seen in the past traditionally. It's a way of overcoming that. The next thing in terms of ring seal is going to be about, you know, the total conform ring. You know, this is a design we developed for larger bore engines and aluminum block engines. In some testing we did recently, with Joe Gibbs Racing with their Desert Off-Road truck engine, which is an all billet aluminum block big bore engine, by going from a 0.8 millimeter diamond finish ring to a 0.8 millimeter diamond finish total conform ring. We cut blow by in half. And the thing is, those radial notches in the back of the ring allow the ring to conform locally to the irregularities in the bore. And think about it, the larger the bore, the more area there is on the bore between the studs, right? That help, provide that strength to the bore. So that larger the span of the bore, the more it can move. Just like, if you've got a 1/4 inch diameter stick and it's 3 inches long, it's gonna be pretty hard to bend it. If it's 12 inches long, it's a lot easier to bend it for the same wall thickness. So when you look at those big bore engines, that's where there's more distortion. The total conform ring can keep that seal. It's all going back to, let me get here, leak path number 3. The gas ports, total conform are about addressing leak path number 3 to get it to be the ring to be able to seal up against a cylinder wall. And then the next thing is you have to have the cylinder wall flat, right? You got to have the right surface profile, surface finish on the ring. I know we're getting close to time, and I'll also say that Keith, in his presentation next week in the super webinar, he is going to cover honing in great detail. So what I'm going to do is I'm going to kind of skip through this a little bit. That's the idea, is that you need to have the right surface finish on the wall for the ring to seal to. When you do all the things the ring to get it to seal the wall, you have to have that correct surface finish. Back talking about the gasket, it's really that surface roughness here underneath. Those valleys are what hold the oil. Proper lubrication is the right oil, right place, right time, right amount. You got to have enough oil in the cylinder bore to be able to be that gasket between the piston groove, the piston ring, and the cylinder wall. All that has to be sealing up together. You got to have the supply, and it's the valley that allows that supply to be there. And that's the key thing, from the oil perspective, on that, and efficiency perspective, you got to have that ring seal. Like I said, I kind of skipped through this because Keith's going to touch on it more. Another good real world example of that is back to the flat tappet cam. You can see pre-break-in versus post-break-in right there, that change in surface finish. But there's still those valleys, even on a flat tappet cam, to provide that retention, a place for the oil to be, so they can continue to lubricate and help see, protect that cam face. So really, break-in procedure is the last thing I want to touch on before we run out of time. I'm not sure if we can go, how far we can go over, Rob and Amanda, but I don't have anywhere else to go if no one else does. But really, when it comes to break-in procedure, if you have a dyno, obviously what you want to do is get load on the engine. Cylinder pressure is what you have to have in order to get the rings to mate to the cylinder wall. If you don't have a dyno, you need to drive the car. Get it up a temperature, get everything heated up, moving around, expanded properly, then drive it like you stole it. That's so important. People that baby engines, you can't idle an engine and get it to break in. It's not going to work. You got to have cylinder pressure. Number 2 is you need to change the oil in that first couple hundred miles. It's really, really important. There's 10 times more wear during break-in than there is any other time in the engine's life. So you want to get that debris out of the engine so it doesn't cause abrasive wear throughout the engine and damage surfaces. And then number 2, or third thing is you want to use a low TBN oil. We did a webinar back in January that talked specifically about that, that really gets into the details. I can kind of hit the highlights. One, should you use a synthetic oil for break-in? The simple answer is no, not because it's synthetic necessarily, but because typically those oils contain friction modifiers that are going to reduce friction, which is not what you want, and they typically have a higher TBN because they're designed to live a long time in the engine, and high TBN, high deterrent emergency works against ring seal. And we saw that, from some dedicated testing we did. If you look at the amount of oil in those exhaust ports, the higher the TBN, the more oil, the longer it is taking the engine to break in, right? So low TBN accelerates that break-in process, speeds it up, so it seats in quicker, which is going to be a good thing, because you don't want oil in the combustion chamber, because it can cause detonation. We've already proven that, and that's obviously a big issue with direct injection engines. The higher the combustion pressures, the higher the compression ratio in the engine, the more tendency there is for knock and detonation, and oil in that environment lowers the octane value of your air fuel mixture, increases knock tendency. So you don't want that. So you want that lower TBN oil, especially in high compression engines. And we also were able to verify that at Joe Gibbs Racing. You look at the high TBN oil, and the blow-by was 21.2, horsepower is 668. Swap it over to a low TBN oil, and it's 18.9, 671. Now, the trick here in this is we actually ran the low TBN oil first, right? So all the data we have over all the years points to low TBN oils are better for braking. It speeds everything up. It helps things seat in better. I saw that myself with a Nikasil cylinder, bore engine, which is going to be the most notorious type to break in. The engine tomorrow we're going to be running in, that 250 single cylinder engine, is also Nikasil, right? And I'm going to be using driven BR30 to break it in, because I know that oil is very low TBN, high zinc. It's excellent for ring seal, especially in Nikasil engines. But what we're going to do is we're going to get it at the temperature. We're going to load the crap out of it. We're going to run it hard. We're going to change oil. We're going to do all those things. And I'm probably planning on doing that on Facebook Live tomorrow too. So hopefully everything works out weather-wise and we don't have any complications. And around this time tomorrow, we're doing that. But we've seen this process myself and that engine, that if you do the right things with the right oil, follow that procedure, you're going to get results that are good. We had showed this in the previous webinar back in January, but it's worth repairing again. If you want to know what the TBN value is of different oils, there is a report at speeddiagnostics.com /total seal that has detailed analysis of very many different brands, like 26 different brands of oil, that list all the characteristics from the ZDP levels, the TBN values, and all that. So all that information is there, so you can make your own decision. At Total Seal, we're not recommending any one brand. We're not going to pick a brand. I said, well, I'm going to do for my engine because that's mine, right? And that's my choice. I happen to have a whole lot of confidence in that product because I formulated it. It's mine. I believe in it. Simple as that. All right, to kind of summarize it, to get to the end, why does all of this matter? All right. Well, one, from an efficiency standpoint, you go through all the effort, spend the money. You want the engine to be the best that it can be. Efficiency is important. But beyond just power, that investment, that durability, you can't win the race if you can't finish the race. Motor oil has two enemies: blow-by and heat. You think about in a stationary, industrial turbine engine, the oil in that engine uses the same base oil that's in motor oil, same base oil that's in gear oil, transmission fluid. That industrial turbine engine, that will live for 10 years before they change the oil. You can barely go 10,000 miles, in most engines where we got to change the motor oil. But you can go fuel for life in a transmission. Why? They all have heat, right? They all degrade the oil eventually, so you have to change it eventually. The difference between an internal combustion engine, a turbine engine, and a transmission is blow-by. The more blow-by you get, the shorter the oil life, period. End of story. So that's why ring seal is so important, because if you can get better ring seal, that means you have less blow-by, which means your oil will live longer and work better. I can tell you one thing that I've seen in working with my daughter Caroline, that can't handle the day-to-day operations, the speed diagnostics. When she has a sample that she needs my input on, 99 times out of 100, there's a high level of fuel dilution. It means that the tuning's wrong, or there's something that's happened. When you get high levels of contamination in the oil stops doing its job. That simple, So that's why it's so important to get good ring seal. And there's more to it than just the rings themselves. Obviously, if you have a really bad tune-up, it's going to destroy it. But it all works together. The goal is to make the engine as efficient as possible. And to do that, you have to have good ring seal. And if you have good ring seal and the engine's running efficiently, it's going to live and run for a long time. So with that being said, that's the presentation for the day. I'll be happy to answer any questions anybody has.
Super, thanks, Lake. That's a great presentation. Really good information, and we do have several questions. So we'll start here with the first one. Let's have a look here. This gentleman's asked, when you crosshatch the cylinder wall, is it recommended to do the entire cylinder wall, or can we only do halfway, or only at TDC, or what's your thought on that?
I would do the whole, because the entire travel of the ring, in the piston is going to require having the surface finish being correct. Obviously, there's been some work done, with like dimpling and things at the very top near TDC to try to, have a different texture in the area that needs it the most versus others, but I'd say, for the most part is that, bang for your buck, time invested, hone it the entire travel, have the same finish, that way you've got the right finish for near TDC, then you have a finish that can provide the most protection, the best sealing performance for the entire length of travel, even if you don't need it.
All right, super. Another one for you. In Canada, it says here, we use high concentration of ethanol, methanol for octane in our pump gas, 93 rated super premium. Are there any special considerations when running gapless rings in a street performance Gen 3 Hemi stroker build with 11.25 to 1 compression ratio?
Well, the nice thing is that a gapless ring, because of that higher ethanol content in the fuel, it's going to make the engine's going to run richer, right? It's going to tune it a little bit, and as you run more ethanol in the fuel, you will typically have to run a richer air fuel ratio because the amount of oxygen that the fuel brings with it, right, it requires that. So because of that, the gapless ring is a benefit, because when the engine's cold, man, that's really, where one of the big advantages of the gapless ring is when the engine's cold and the clearances are the most, that's where you're going to get more blow by, because the operating clearances at that point are the widest, and the engine's cold, so your distillation of the fuel is going to be less. So if you think about, the sprint cars and that kind of stuff, they don't really need the gapless when the engine's at wide open throttle, and the engine's at full temperature. The operating clearances then are really, really thin, and you got all the heat working, to keep the methanol out, and the methanol's evaporating. It's tuned right. It's when it's idling around and it's cold, that's where the gapless ring, provides the best contamination control for everybody. So that's where, a street build like that, especially in Canada, that's where a gapless ring will be at its best, actually.
All right. Next question for you, Lake. What is the difference in formulation between braking oil and racing oil?
Aha, great question. I love that. Thank you, whoever asked that question. So I think this is the slide to get to. Yeah, perfect. Yeah, this is the one. So these two right here, I'm pointing at the screen. You can't see me pointing at the screen. But okay, so if you can read that chart on the screen, if you look at SDS 649, that's a sample ID. So that's the third one from the left, and then the fourth one from the left, right? So the SDS 469 versus SDS 470. That's a direct comparison of the GP1 braking oil to the GP1 race oil. Now, just forget about the viscosity part of that, because it doesn't really matter at this point, because one's a 30, one's a 2050, right? So you can't compare those two. But look at the additive section, okay? So we're going to walk through that real quick. Okay, so when you look at the calcium, sodium, and magnesium, that's your detergent package. Again, for break-in, you want a low detergent package. That way the ZDP can do its job in terms of helping to assist that chemical break-in, and you don't want the TBN working against the rings bedding in. So you can see that the calcium level of the GP1 break-in oil is 209, no sodium, no magnesium. But the race oil is 2100, so it's 10 times more. Well, because during that initial break-in, everything's clean. You're not going to run it for super long time, so you don't need a high level of detergent. But once you've broken it in, now you want to maintain a clean surface, so that balance changes from break-in to race. The detergent level comes up some to maintain cleanliness. Other thing you're going to see too is your zinc phosphorus levels there. They're really not that different. I mean, a little bit more actually for break-in, because break-in oil is really kind of like putting down primer before you put down paint. Think about in the old days, growing up around NASCAR and stuff. Yeah, especially in the late '90s when it was the paint scheme of the week, and that was before we had decal wraps and you actually had to paint cars. There was always work to be done in the body shop. So when I worked at Melling, I helped out my buddy Craig Smith, who was the head paint and body guy there at Melling, and we had 9 different paint schemes in 1999, and we had to paint all those cars. So we were painting cars a bunch. I'd go back there and help them out, and you put down primer before you put down base, before you put down clear. If you skip the primer, you can still get the paint down, but it really wouldn't hold on the car correctly, and it really wouldn't look good long term. If you put down primer first, then you did all the surface work prep, then it worked right. That's kind of what you're doing with break-in oil, is you got a little more ZDP because that surface is still fresh. It's clean, it's new, which means there's no anti-wear film on it. So that higher level of ZDP initially for break-in with low detergent allows that primer effect, right? You're getting the anti-wear film established on those parts, then you're just maintaining it afterwards. Then you can add in with the race oil. The key thing is you're going to add in the moly and the boron. Those are your friction reducers. So that process is part of the synergy, right? If you think about what we were doing at Gibbs there in the mid 2000s, with using break-in oil and then race oil, and we were using these stainless steel PVD coated thin rings. The break-in oil in that process of running an engine at load and cycling and all that was designed to do was allow to use that thinner ring, chemically assist the ring to seat in properly, so we would get the least amount of friction, low blow by, and then once it was established, then we could bring in extra friction reducing agents in the race oil to optimize the total package, right? Again, back to, hey, 46% of the friction is the ring. That still means there's other friction to be had by reducing viscosity, by improving the lubricity of the oil through friction modifiers. So that's where that whole process, there's synergy of working them all together could really unlock the most and the full potential of the engine, which we did and won a bunch of championships doing it. Still proud
Super.
of that.
That's awesome. No, that's awesome. All right, here's one for you again. So I understand the benefit of thin rings. A lot of companies are thinning the oil ring as well as second rings. How are you controlling crankcase pressures and oil control in higher horsepower wet sump street engines? not LS engines. That's a different issue.
Well, oil ring tension does matter, obviously. And then I think one of the nice things, if you think about oil control isn't just coming from the oil ring, the three-piece, oil control ring. The second ring, 80% of its job is oil control. So if you think of the three-piece oil ring as the gross or bulk oil control, the second ring is going to be your fine oil control. So we really like a Napier second ring. A ductile Napier second ring is a fantastic tool for helping oil control. Back to the engine at Shavers, that was an 11-pound tension three-piece oil control ring, but we were running a ductile Napier second, and in that engine, without any vacuum, we had essentially zero oil control problems. Once it was broken in, right? If you tried to break that in with a high TBN oil, it hated life. But that really was an issue because of the high TBN. When you had the correct break-in oil, you can have good oil control, even in a street type engine like that, as long as you have not too low a tension oil ring, but you're also complementing the oil control ring with that ductile Napier second, and balancing those two. If you utilize those two rings together, you can really achieve good oil control, and that makes a big difference.
All right, here's another one.
Hope that answers the question.
Okay, all right. So here's one. With the gas ported rings, will they work with a naturally aspirated nitro-fueled air-cooled motor, or will the rings lose their properties? Also, maybe you mentioned it, but I missed it. What type of metal is used to produce them?
Okay, so when it comes to the gas ported rings, we've got a couple of different options. For your just street high performance guy, a really easy upgrade if you're using shelf pistons that are not gas ported. Say they're a lot of those shelf pistons are going to be, either a 5/64 or a 16th, ring groove design. We have, ductile moly, cast rings that that are gas ported. They're on the shelf. Because of the size of that ring, there's so much material there. It's very easy to go in and put in very thin, shallow gas ports in that ring that do not compromise the integrity of that ring to the point where it's a problem to be used in a street type application. And of course, because them being ferrous materials, the detergent in the motor oil is going to do a great job keeping them clean, plus that contact in the ring. So you can use those gas ported ductile moly, the CR set rings on the street without a problem. Now, for the performance engines, like the competition engines, that's where we really recommend going with the stainless steel, the AP steel rings. So that's 440B stainless steel, and those work really, really good, up to about 1,500 horsepower. And again, all the benefits of gas porting, but those benefits last longer, less bore wear, more even bore wear, and you can do that with the 440B stainless. The level beyond that, if you're talking about really high horsepower nitrous stuff, now you're going to get into the M2 tool steel. So obviously we've got M2 tool steel rings we've been doing, for the pro mod guys and stuff like that, and they are fantastic because that material is just a better material. As that power density increases and the severity of the environment, and you think about, with nitrous versus a gasoline application or even a methanol application, what's unique about nitrous is, that it's a gas, because it contains oxygen and it's in a gaseous form like that vaporizes so easily. It's so aggressive in terms of the flame front. And all the guys who do, and I'm not a nitrous tuning guy, right? I just know people who are, and slept at a Holiday Inn last night, right? But, you know, because nitrous has such a hard impact, that's why you want to use the M2 tool steel. The tool steel material is able to handle that sudden impact, that harsh environment better than stainless steel can. Now, obviously, when you're at lower levels of nitrous and boost and all that, the stainless steel is going to be better than ductile moly because it's going to have more elasticity, better tensile strength. But then when you get to the really high, crazy applications, that's where the way to achieve it isn't a thicker ring, it's moving the tool steel and allowing that conformability to be in there, because there all that distortion, the thinner ring, better material is going to give you better conformability, and that's going to give you the better performance overall. Hopefully that answered that question.
Excellent. Yeah, thanks, Lake. All right, we got time. We're going to do one more question here, and then we'll let everybody sort of get on with the day. So this is a good question. Will aluminum anti-seize cause detrimental oil contamination and introduce bearing surface wear?
Ooh, it certainly could. Any type of solid lubricant, because that's, anti-seize is a great example. It's a compound. It's got a lot of different additives in it, or materials in it, and they are solids. Those are required, in a lot of places in the engine to assemble it properly, but you really want to minimize the amount of that can be, exposed to the oiling system. Yeah, I know several years ago, the guys at ARP asked me to talk to them, about that, how assembly lube is going to be interacting with the motor oil, and can it have a negative impact on the engine and how it performs? And the answer is yes, it can. So you want to minimize that, which is also one of the reasons why it's important to change the oil pretty soon, right? You get in there and you do your initial break-in, you get things going, get that stuff out of the engine, because some of the stuff in there is going to be good, some of the stuff isn't necessarily ideal. So yeah, it's a good question, and that's the reason why you want to change the oil more regularly, especially early on in the engine's life, to get stuff out.
All right, thanks, Lake. We do have several more questions. We've got a few here, but what we're going to do, again, just to respect everybody's time, Lake, he's really good at getting back to everybody, so we're going to pass those along to him, and just remind everybody that we will see Lake again next week in our super webinar on May 15th. And again, if you're not registered for this one, this is a must-see. I mean, to have all four of these gentlemen,
that'd be worth it.
Exactly, to have Billy and Keith and Lake and Ben all on one venue is phenomenal. So we're looking forward to next week. And again, we'll be talking to everybody next week on that one. I'm going to flip over here just a minute for Amanda, and she's going to tell you about a little bit of contact information to reach us. And Lake did mention today that if anybody's looking to get a copy of his presentation, let us know. Again, just put that in the questions box there, and we will get you a copy of that. So Lake, we always respect your time. We appreciate it. You're a huge help to us, and we look forward to talking to you again next week. Thanks again.
Oh, thank you for the opportunity. Thank you, everybody that tuned in to watch today. I really, really appreciate it. And thank you again for the opportunity. Everybody stay safe and have a great day.
All right, so I'll flip back over to Amanda. Thanks again, Lake. Have a good one.
All right, bye.
All right, a couple of quick things for you guys. First off, you will get a follow-up email. This email will contain a link to today's recording. That is yours to use as you would like. You can pass it along to others, rewatch it at your convenience. It's all yours. Next up, there will be a survey when you leave the webinar today. Please take a moment and fill that out. Let us know how we're doing. If you have any additional questions for us or Lake, you can put them there as well. And lastly, you'll see our contact information is listed there. You can reach the AERA team at 815-526-7600, and you'll see my email addresses listed there along with Rob's, Steve's, and Karen's. We thank you again for your time. We appreciate it, and we hope you all have a great rest of your day.